Torsion refers to the twisting of a cylindrical object and a torque or twisting couple is applied to it. This is a common phenomenon in mechanics and engineering, particularly in the analysis and design of shafts, axles, and other cylindrical components that are subjected to rotational forces. Let's explore the concept of torsion and the role of twisting couples in more detail. Torsion is a type of deformation that occurs when an object, typically a cylinder or a shaft, is subjected to a torque, twisting force, about its longitudinal axis. When torsion is applied, the material experiences a shearing stress that results in angular deformation or twist along the length of the object. The deformation caused by torsion is proportional to the applied torque and is inversely proportional to the object's resistance to torsion, which is characterized by a property called the torsional rigidity or the torsional modulus of elasticity. A twisting couple, also known simply as a torque or moment of torsion, is a pair of equal and opposite forces applied at a distance from the center of rotation, resulting in a rotational force. Mathematically, the torque, Tt, is calculated as T equals FRT equals FR, where FF is the applied force and RR is the distance from the center of rotation, axis of the cylinder, to the point where the force is applied. The twisting couple induces shear stresses in the material, causing it to twist. In a cylindrical object subjected to torsion, the distribution of shear stress varies across the cross-section of the cylinder. It is maximum at the outermost surface and decreases linearly to zero at the center. The polar moment of inertia, Jj, characterizes the resistance of the cross-section to torsional deformation. The angular deformation or twist, theta, of the cylinder is directly proportional to the applied torque and the length of the cylinder, and inversely proportional to the polar moment of inertia, theta equals TLGJ theta equals GJTL. LL is the length of the cylinder, and GG is the shear modulus of the material. Torsion analysis is essential in the design of components like drive shafts, propeller shafts, and other rotating machinery parts. Engineers calculate and design these components to ensure that they can withstand the torsional loads without failure, taking into account material properties and geometric considerations. In summary, torsion is the twisting of a cylindrical object when subjected to a torque or twisting couple. Understanding the distribution of shear stresses and the resulting deformation is crucial in the design and analysis of cylindrical components to ensure their structural integrity and performance in various engineering applications. The bending of a beam, such as a cantilever beam, occurs when a transverse load or force is applied to the beam. Bending results in the beam deforming, with the top surface typically experiencing compression and the bottom surface experiencing tension. The bending moment is a key concept in analyzing the bending of beams, and it measures the internal distribution of forces within the beam. The bending moment at any point along the length of a beam is a measure of the tendency of the beam to bend or deflect at that point. It is calculated by multiplying the force applied perpendicular to the beam, the load, by the distance from that point to a chosen reference point, usually called the moment center. The formula for calculating the bending moment, M, at a given point on a cantilever beam subjected to a point load, F, at a certain distance, x, from the fixed end is, M equals Fxm equals Fx. Where, mm is the bending moment in Newton meters, Nm, or foot-pounds, lb/ft. Ff is the applied force, load, in newtons, N, or pounds, lb. The magnitude of the bending moment varies along the length of the cantilever beam and is typically highest at the location where the force is applied. For a distributed load along the length of the cantilever beam, you need to integrate the load over the length to find the bending moment at a specific point. Cantilever beams are commonly used in engineering for various applications, including in the construction of buildings, bridges, and mechanical systems. Analyzing bending moments and shear forces in such beams is essential for ensuring they can support the loads they will experience in their intended use. Engineers use this analysis to design beams with the necessary strength and stiffness to meet safety and performance requirements. A centrally loaded beam is a type of structural element or component that is subjected to an applied load or force that is centered or concentrated at a specific point along the length of the beam. This type of loading is common in various engineering and construction applications, and understanding how beams behave under centrally applied loads is crucial for design and analysis. In a centrally loaded beam, the applied load is typically concentrated at the midpoint or center of the beam's span. However, it can be applied at any point along the beam's length, as long as it is symmetrically distributed with respect to the beam's centerline. The central load can take various forms, including point loads, applied at a single point, distributed loads, spread over a specific length, or concentrated moments, torques. When a beam is centrally loaded, it experiences bending. The beam will deform and bend under the influence of the applied load. The amount of bending depends on the magnitude of the load, the beam's material properties, and its cross-sectional geometry. The bending moment within the beam varies along its length. At the center of the span, where the load is applied, the bending moment is typically at its maximum. As you move away from the center, the bending moment decreases, reaching zero at the supports. In addition to bending moments, centrally loaded beams also experience shear forces. These shear forces distribute the load transversely along the beam's cross-section. Centrally loaded beams undergo deflection or deformation. The amount of deflection depends on the applied load, the beam's length, and its stiffness, related to its material and cross-sectional properties. Engineers and architects need to consider centrally loaded beams when designing structures like bridges, buildings, and mechanical systems. They calculate and analyze the stresses, deflections, and other factors to ensure that the beams can safely support the loads they will experience in service. Centrally loaded beams can be found in various shapes and configurations, including simply supported beams, cantilever beams, and continuous beams. The specific type of beam and its boundary conditions, example, how it is supported at its ends, will affect its response to central loading. Analyzing centrally loaded beams involves applying principles of structural mechanics and using equations of equilibrium, such as those related to bending moments, shear forces, and deflections. Engineers use this analysis to make design decisions, select appropriate materials, and ensure that structures are safe and meet performance requirements.